All right, so I am from NASA Johnson Space Center down the road. We focus on human spaceflight. And so the talk I'm going to give you here while we're talking about robotics and AI, what we're really trying to do is enable our astronauts to move further out into space. So right now we have the ISS. Our astronauts go and visit for typically about 6 months at a time. This is Gateway. It is kind of where our ISS astronauts are going to go for their rustic camping vacations. It's going to be in orbit around the moon. The cool thing about Gateway is that it is meant to be just that, a gateway to lunar and Martian exploration for humans exploring deep space. And so it's very exciting for that reason. But we're going to try to challenge ourselves, even though the moon really isn't that far away in the cosmic sense. We're going to try to challenge ourselves by pushing that technology that we would need to be able to have humans go further out into space. For one, humans are only going to be on board this Gateway 30 days per year. So that means that this complex spacecraft is going to be flying around the moon constantly, 11 months out of the year. Stuff is still going to break during that time. As you all know, if you own houses or cars or whatever, they always break at the most inopportune time. Things do. So having something available on board that spacecraft to be able to maintain and caretake that spacecraft is very important. We're also going to challenge our communications abilities. So the astronauts, when they go to Mars, are going to have just physics not in their favor. They're not going to be able to talk to Earth with all of the cloud and the expertise and all of the brain power that we have down here. They're going to be stuck with just their brains and whatever we send up with them. And so we really want to make sure that in those cases we're doing something good for them, that they have the ability to make decisions, even if the light time difference between communication with the Earth is 40 minutes or greater. So I'm going to show you some videos. So I was introduced, this is Robonaut. This is an experiment that we did aboard the International Space Station several years ago at this point. I think it's 2012 or 2013. And we were basically just trying to get our robot, which is a dexterous upper body humanoid at this point, to do something dexterous. So we were commanding from the ground. Latencies weren't bad, maybe a second. And we had camera views from the eyes, we had camera views from the side, we had astronauts who could come by and tell us what was going on. But this was really hard. It was very hard for us to do. There's like 5 people in the control system on Earth just inspecting every little motion what the robot was trying to do. It's basically being teleoperated. We had some tools that were available to us to try to make that work easier, but it wasn't. It was a very intense set of motions. It did succeed. It did something that was really cool. I mean, these are small little quarter-turn fasteners, and it's moving a flexible blanket, which is something that was very state-of-the-art, particularly at this time. But it was a success, but limited success, if you ask me. So we decided to think about that more, because when we go further out, we're just not going to have the ability to have 5 people sit behind a robotics console and have the robot do repairs when somebody's not on board the Gateway, and that be their full-time job. It would just be too intense. We wouldn't get enough done. So we started making more tools that would kind of help the user go up a level, so that the robot itself would be able to figure out more of that low-level stuff and have the manipulation, the translation here. We're doing some path planning with collaboration with Rice University, automatically detecting where these handrails are and grasping them. And once we get to the end here, you're going to see that same Softgoods panel. So this is 2015, so it's 3 years ago now, and it was a couple years after we had done this on the ISS. And you see some tools down at the bottom here. These tools are what we had been developing, and we had the benefit of this thing called the DARPA Robotics Challenge, which was really cool, and it helped us see how other people were also dealing with remote dexterous manipulation when they had network issues. And this sort of technology was actually developed by several different folks all at the same time. We came up with it, and so did many other groups across the world. And it's something called affordance templates, and I'll talk about it a little bit more on the next slide. But basically what we're doing is we're putting the robot in, a model of the robot in with the, registered with its data, what sensor data it's getting, and also models of objects in the environment. And these models are what we were using to encode interactions or affordances of how it can be manipulated. And so this is a picture here, a little bit more of that first round of how we did affordance templates. And in the beginning, there was no AI really, and this is all human, manipulated. We'd get those models and we would say, this is how I would use the robot to go grab that, and that's great. And then we'd plug them in as the task ensued, right? So we would have, okay, now we have to do the quarter turn faster, now we have to pull back the blanket, all those sorts of things. And that was still a lot of work. And so we were like, we're lazy, we want the robot to know a lot more about this kind of stuff. And so we introduced a tool called Task Force that allowed us to then start wrapping together, like putting together like scripts, if you will, but they weren't just scripts. You could add in lots of different affordance templates, but you could add in supervisors that could say whether your affordance, your manipulation succeeded or failed, or what state of failure you were in. You could have vision processing. You could do a lot of different things that would kind of all plug together into this activity that you would, or task that you would do in Task Force. And then beyond that, we thought, well, this is cool, but this still isn't quite the full picture. We really want the whole picture to be, the whole task to be taken care of. This robot should be able to handle the things that the spacecraft needs it to do, and the spacecraft should know what needs to be done. And this is influenced by people on the ground, of course, but the spacecraft's going to have some priorities on what it needs to do to keep itself safe, and it should have the awareness to be able to identify when things go wrong, what those things are, and what are we using to solve it. And so the framework at the bottom there was how we thought about that autonomy loop to close that loop for us. And so this is a fairly recent video. It's about a year old. I like this video a lot. It's one of my favorite ones. So Robonauts, I should have introduced before. It's in a gravity offload facility down in my building at NASA. Its task here is to climb through the spacecraft, open a hatch to a logistics module, and then go get a cargo transport bag. So that's how we send up logistics from inside of that other module. And so we have some mock-ups here because we're not in space, but it's doing some really cool stuff from a robot sense, in that it's holding on with 2 legs and from above, and it's still being able to do path planning and move its body with all those constraints and do valve constraints and that sort of thing. And that's really cool, and it looks kind of like it just should be able to do this, which I think is also cool. But the interesting part about this video really is my operator that's there on the very left-hand side. We went from 5 really intense operators to one guy who's checking his phone, drinking his coffee, picking his nose, right? He is not intensely involved in what's going on. He's there, he's supervising, he's helping them out. When the robot has a problem, you'll see him every once in a while go and do a couple of mouse clicks on the computer. The robot now, though, is smart enough to know when it has a problem. So it's able to go and do this task in a similar commanding method than we would want to do with an astronaut, right? So astronaut, please go into the logistics module, find bag X in bay 3, and bring it to this point. And that's the level at which we're hoping to be able to give those commands, not just to the robot, but to the spacecraft, and have the spacecraft have the smarts to know that it's able to do those things, and to know when it's not able to do those things and needs extra input into the system to be able to do that. So it does go and get this bag here. And I think in the interest of time, I'm going to keep moving on. So this is obviously a great place for dexterity. I can't hear it. Sorry, hold on.
No problem. Let me try and find the adjustable bridge.
So Robonaut talks. It's kind of cool. So that's using, I think it's Watson and Google together. But the idea here is that this sort of interface is really ripe for AI, right? There's a lot of ways we can use learning, artificial intelligence to be able to do this. So what it's doing now is, that's Phil, and he has taught the robot what a set of tools are. And these tools, when they're presented to them at any point, they're able to identify that that's the tool. It's able to associate it with a model in the affordance templates framework, and that affordance template has encoded into how that robot would actually go and grasp those tools. It can happen at any point in anything. So there's nobody behind a computer at this point. Phil is running the robot. And so the robot is smart enough now, and he could even talk to Phil and say, I don't know what to do, so that we didn't show this on this video, but if it's outside of its reach or it can't find it, it just tells Phil that, and Phil can then go fix the problem if he needs to. So this is all great, but what we've been working really hard on is incorporating the technology that we've been doing with our robot into the entire spacecraft. So this Gateway is something that I've been working a lot on, and what we're trying to do with Gateway is, one, we'll have intravehicular robots, so robots inside that are servicing the station, but we also want to have this vehicle systems manager. We want to have this intelligent entity that's kind of on board and is above a distributed hierarchy of intelligent agents that might be looking at systems down below. And so what we're doing with this is we're putting together a lot of different models of different levels of abstraction. These models might have different, they could be learned agents, they could be linear regressions, they could be what have you. And we want them all to work together to be able to solve problems on a spacecraft level. And so we've been working on a framework that allows us to do this with a careful design of where the locus of authority, or like who gets to do what, is. And we're also working really hard on making sure that it's safe. And so the verification of our autonomous systems and our learned agents and all those sort of things, that we are always satisfying safety specifications that get laid out, flight rules, constraints, what have you, is a key part of our framework and a key part of what we're looking for when we are trying to make these intelligent systems to be able to control and control our spacecraft. So last slide here, just in conclusion, we've got some really cool challenges coming up, but I've really been interested in hearing the talks so far today and the customer-based concepts that you all have had. I think one of our biggest challenges is we don't have the cloud, and we do have these really high reliability, trustworthiness kind of factors that the safety and security of all of your taxpayer dollars is up there, and obviously of the astronauts that may be on board as well. And so we've got a lot of interesting questions that we need answers to that we don't necessarily know, but we're working really hard on trying to understand what role these technologies can reliably play, how we can make these systems trustworthy, and how we can design these for good teaming, both with the operators on board, the crew, and the operators on the ground who don't have the situational awareness that they may want to have to be able to really influence and help these problems. Does anybody have any questions?